Hello everyone and welcome to the first part of this week's lecture. So today we start with ensemble learning. So the idea of ensemble learning is to select a collection, or essentially ensemble in French, of hypotheses h1 through hn and combine their prediction either by taking the average or by taking a vote if we're doing classification, or by any other level of machine learning. So we can actually train a machine learning model to take the output from all these regressions and give us one final output if we're not happy about taking the average or taking a straight vote. So here we start with what we call the base model, which is the individual hypotheses. So you can say, for example, my base model is going to be a classification tree or a neural network, for example. And then you want to train a lot of these models, but obviously they have to be different in some way in order to give you some variation in their prediction. If you train all the models from the same family, so say for example we do classification trees, if we train 10 classification trees, all with the same data and all with the same features, we're going to end up with the same prediction. So we're not really getting any advantage from creating this collection of classification trees. So we have to find a way to create this model, but to make sure that they're different. So the reason why we use ensemble learning is to reduce bias, because ensemble can be more expressive. So there's less bias than the base model. So obviously, if one model is too simple to capture the dynamics of the data you're training on, then 10 models will probably have a better chance of capturing this dynamic. And also reduce variance. So it is hoped that it is less likely that multiple classifier will misclassify. So we're hoping that by doing ensemble, we're not going to overfit one single model to the data. So let's see how this approach works. So one way to do ensemble learning is what's called bagging. So in the case of bagging, what we do is, say for example, we have 100 possible training features. So what we do is we select a sample of these features from the original training set. So let's say, for example, we're going to select 10 different training sets. Each time I'm going to select out of the 100 features, for example, 20 random features. And I'm also not going to train on the entire set of records I have, all the examples, but I'm going to select a subset, n examples from the entire data set. So I'm reducing the number of features, and I'm also reducing the number of examples that are available to train. And both of them are selected randomly. Then I'm going to run my machine learning algorithm using this reduced set of features and this n examples to get one hypothesis. Now I'm going to repeat this process k times to get k different hypotheses. As you can imagine, every time we're resampling from the training data, we're resampling from the feature space, so we're going to end up with a different classification tree or model in general, or hypothesis in general. Now I'm going to aggregate the predictions from all these hypotheses together. So for example, if we're doing regression, then I can get a prediction from all of them and just take the average to say, okay, this is my best outcome. So 1 over k sum over I is through 1 to k of the prediction of all the hypotheses I trained hi. For classification, we can just take the majority vote. So for example, if I trained 11 models or 15 models and 8 of them say class 1 and 7 say class 0, then I'm going to go with the majority. So that's how we generate a set of models that are not the same from the same data. So random forest is one way to do this tree bagging approach we just discussed. Again, we randomly vary the attribute choice, so we pick a different set of features every time. And at each split point in constructing the tree, we select a random sampling of attributes. So given n attributes, we get the square root of n common number of attributes randomly picked at each split for classification and n over 3 for regression. This is a mathematical finding, you don't have to worry about it, but essentially is just another way to increase the variability in the prediction from your classification trees, which is the most important thing to make sure that ensemble learning works for us, is to make sure that the models are not acting as a herd. They're not all going in one direction, but rather that there's variability in the prediction. So another concept that's very popular when using ensemble learning is boosting. So the idea behind boosting is that so far we said all the training example when we calculate the loss function, they all have the same weight. We then give different weights to different examples. In boosting, the idea is to actually give different weights to different training records depending on how difficult it is to predict the correct class for that specific record. So we increase the weight for the records that have been misclassified and decrease the weight for the records that have been correctly classified. And the idea here is by increasing the weight for the misclassified records, we're forcing the next classifier in the ensemble to do a better job on these cases where we were not able to make the correct prediction in the past. So by doing that, essentially I'm trying to increase the probability that my final ensemble with all the models will do a good job, not only on the easy to classify cases, but also on the hard to classify cases. So this approach is called boosting and is very popular. And one of the most popular algorithm is called ADA boost. There's also a very popular algorithm called XG boost that applies a similar idea. And they both essentially try to continuously do that from one model to the next, is to change the weight for the misclassified examples to increase the weight for these examples and reduce the weight for the correctly classified examples. And AD boost will return a hypothesis that classifies the training data perfectly, is guaranteed for large enough K. So if you include a large enough ensemble, then ADA boost is guaranteed to give you a correct classifier over the training data. And of course, it boosts the accuracy of the original algorithm. So a simple tree will never beat an ADA boost ensemble of trees. And it overcomes also any amount of bias in the base model. Now, the only condition for all this to work is that your base model is better than random. So if your base model can't beat a random classifier, it doesn't matter how many hypotheses you include in your ensemble, it's not going to work. So that's why we use classification trees, because they have been proven to use to beat a random guess, of course. So this is a good visual explaining to you how that boosting works. So we start with hypothesis H1 here. You can see that it correct. Here's the weight is the same for all the 4 training examples. 2 of them have been correctly classified with a check mark next to them, and 2 of them with the X next to them have been incorrectly classified. You notice that in the next iteration, I increase the weight for the 2 in the middle because they were misclassified earlier, and reduce the weight for the 2 at the bottom and on top, and then I get H2. Now in H2, only the bottom one has been misclassified, so I'm going to increase the weight for this one while decreasing the weight for everything else. And finally, in the last iteration, H4, you can see that everything has been correctly classified. Again, I increased the weight for 1 and 3, but decreased the weight for 2 and 4. Now the size of the tree down there tells you the weight we're going to give to the prediction of that tree in the vote. So when we do voting, we don't have to give one vote for each tree. We can actually give a higher vote or a more significant weight to the vote of H4 compared to H1, just because we know that H4 has a higher probability of making a correct prediction compared to H1 because it happened 4 iterations after H1. So this is the pseudocode or the algorithm for ensemble learning. You can review it. And so let's finish this lecture then by going over the general procedure for developing machine learning systems. So first, you have to determine your problem, what exactly you're trying to build, and what is the loss function. Is it a classification problem? Is it a regression problem? And what metrics I'm most interested in tracking as the training takes place. Then we collect the data, clean that data, augment the data through feature engineering if needed. If you have imbalance in your class distribution, you have to deal with that by undersampling the majority class or oversampling the minority class. Consider outliers and see how you're going to deal with them. Again, feature engineering, if you can think of some features as combinations of the original features that could help the classifiers, this would be a good time to add them to your training data. Then you decide on what model you're going to use. Are you going to use trees, a neural network, support vector machine, whatever model you're going to use. And typically we use our model based on the ROC curve, the AUC also, which gives us a single number summary of the ROC curve, the confusion matrix if we're doing a classification problem. We can analyze that and decide on what model to use. After we built our model and trained it, then we have to test it, review it, monitor it, and make sure that we understand everything that's going into the input and how to read the output, and then monitor the performance of the model in production, and make sure that we make any adjustment as needed if the data changes or the environment in which we're making the prediction changes or anything like that. So this concludes the first part of our lecture, and then I'll see you in the next part.